Today it is an honor to present our work, Learning Classifiers or Prototypes and Reciprocal Points for Universal Domain Adaptation. It is done by researchers in KAIST RCV lab. To overcome the expensive and time-consuming labeling for a new dataset, unsupervised domain adaptation has been studied to transfer the knowledge of labeled source domain to the unlabeled target domain. Existing domain adaptation methods rely on the fixed relationship between the labeled set of source and target domains, such as closed-set DA, partial DA, and open-set DA. To handle the arbitrary label shift in real-world domain adaptation, a general domain adaptation technique should be required, which is universal domain adaptation. The main challenge of the universal domain adaptation is distinguishing the unknown classes from known ones while adapting to the target domain. To handle the above issue, we use both prototype and reciprocal point. Prototype is the closest representative point for features of a class, and reciprocal point is originally the farthest representative point for features of a class. To deal with the unknown classes, we further interpret reciprocal point as the point for unknown classes. With our proposed methods, trained model can separate known and unknown classes more effectively. The framework of our method is as follows. We use two runnable dual classifiers for prototypes and reciprocal points. Each classifier generates each probability PP and PR. These are gathered to make collaborative probability PC. As shown in following equations, features of each class become closer to its prototype and farther to its reciprocal point. Source domain is trained as follows. Along with two closed entropy losses, we further use loss on and loss split. Merely minimizing closed entropy of reciprocal point classifier can expand the unknown feature space. Therefore, to minimize unknown space, it is required to restrict distance between source and its reciprocal point to be less than R. And loss split is to separate known feature space from unknown one. By choosing a nearest reciprocal point, each source feature becomes more closer to its prototype than any other reciprocal point. To train the model more reliably, we train the model with two phases, warm-up and adaptation phase. During the warm-up, to generate more compact target features, we use KL divergence laws between two different views of target domain. At the same time, two thresholds are progressively updated with moving average for known and unknown classes as follows. In the next adaptation phase, to select more confident and reliable samples, we use multiple criteria, thresholding and consistency between dual classifier. With the selected samples, we calculate entropy losses for known and unknown samples respectively. However, there might be imbalance between them, so we weight each entropy loss term with the number of samples for known and unknown classes. In the end, the model is trained with the overall loss as follows. For the open-set domain adaptation, we can get state-of-the-art performance or comparable to the existing methods. Also, for the universal domain adaptation, we can get state-of-the-art performance for all benchmarks. As a result, we show that our method is robust to the open-set domain adaptation and universal domain adaptation. Thank you for your attention. Please visit our poster for more detailed explanation.